evening. This month we may, I say may, have a really good display of meteors or shooting stars, and we'll talk about those now. But first of all, one news note. On November the 15th, the little planet Mercury will pass in transit across the face of the Sun, appearing as a black spot. This Douglas Arnold photograph shows it going in, and here's Mercury on the Sun's disk. I fear you won't see that from here, and the next one won't be until May 2003. Not important, but interesting. And now, on to our meteors. Now, meteors or shooting stars are not stars. A star is a sun. A meteor is a piece of cometary debris, a tiny particle, usually smaller than a grain of sand, going around the sun. If it dashes into the Earth's air, it rubs against the air particles, is heated by friction, and burns away in the streak we call a shooting star, and there we can see a shooting star trail coming away from the stars in the plough. You can see meteors at any time. These are called sporadic meteors, but there are also meteor showers. As a periodic comet moves along, it leaves a dusty trail behind it, and when the Earth goes through the trail, we have a shower of shooting stars. And those happen many times per year. And the shower is named after the constellation from which the meteors seem to come. For example, the November meteors seem to come from the constellation Leo, and they are therefore known as the Leonids. And they come from a radiant, purely in effective perspective. The meteors in the shower are really traveling through space in parallel paths. And these Leonids, well, they can be really spectacular. They're associated with a comet called Tempel-Tuttle. That goes around the Sun in a period of just over 33 years. And there's a picture of it taken in 1998 by Martin Moberly. It was last close to us in March last year. And as the Earth goes by, well, for a few years either side of the comet's path, we may see a good shower of meteors coming from that comet. We expected one in 1998, and in a way we got it, but not quite as we expected. There were some major surprises. And over now to our meteor expert, Dr. John Mason. Welcome back, John. Well, what happened in 1998? Things went wrong, didn't they?
Yes, we expected the peak of the Leonid shower last year, the time when we would see most meteors, to occur at about the time that the Earth passed closest to the comet's orbit. In other words, about 2000 hours on the evening of the 17th of November. But what we found was that the peak of the shower occurred 16 to 18 hours earlier than that, at around 2 o'clock in the morning on the 17th, and that was a major surprise. Leonid rates peaked at around 300 meteors per hour. Now that meant that people were seeing some 2 to 3 Leonid meteors a minute, but occasionally they came in bursts of 6, 7, 8 meteors a minute, and things got quite hectic. Here's a lovely photograph of one of those Leonid bursts taken by Lorenzo Lovato, and you can see all the Leonid trails there with Orion on the right. Another surprise was the width of the peak of the shower. We expected the Leonid activity to be concentrated within a time of perhaps 1 or 2 hours, but in fact the meteor activity went on for some 6 to 8 hours. If we look again at the activity curve, you can see that rates were more than 200 meteors per hour for around about 8 hours, and indeed more than 100 meteors per hour for getting on for 36 hours or so. So that was another surprise. The long-lived nature of the shower was best shown, I suppose, by the radio observations. Now, when a meteor occurs in the upper atmosphere, it leaves a trail of electrically charged particles behind it. These can reflect and scatter radio waves, and that's what we can do. Now, here we have a chart record of radio observations made by Tim Wright from Pagham in Sussex. And as the meteors scatter the radio waves from the transmitter in Poland to his receiver, you get this array of spiky signals. Now you can see right over there, from about 11 o'clock on the evening of the 16th, Leonid activity was very, very strong, and peaking in the early hours between 1, 2 o'clock in the morning and about 6 in the morning, but continuing after daylight, 8 o'clock, 9 o'clock, 10 o'clock in the morning, and only subsiding as we got towards midday on the 17th. So really a very broad peak of activity indeed.
I think Tim Wright did very well on that one, operating from Pagham, quite near me. A very valuable record, that. Interesting to note also that those Leonids were particularly rich in very bright meteors.
Yeah, that was another surprise. We expected the shower to be fairly rich in faint meteors, but we found there was a very high number of fireballs. Those are meteors brighter than the brightest stars and planets, And here we can see a lovely photograph of a fireball taken by Terry Platt. Now, normally the Leonids are rich in faint meteors. Last time there was this preponderance of bright Leonid fireballs, very spectacular for those that saw the shower. Here's another lovely Leonid fireball photographed by Lorenzo Lovato, seen through thin clouds.
That's a beauty.
It is. Now, I, of course, as you know, went to India to try and catch the main peak, but missed it, of course, because it was 16 to 18 hours earlier than expected. But we did get some quite nice bright Leonids after the main peak, and this video clip shows a number of them streaking across the sky from left to right, Orion in the top right of the screen there. And I might say that camera was mounted on the roof of a house in remotest Rajasthan, with the only electricity supply coming from a rather rickety generator.
At least you saw something. I was totally under cloud. Well, why do the Leonids behave like this?
Well, it turns out that the structure of the Leonid dust storm that causes the shower is much more complex than we previously thought. You see, the dust from the comet has spread slightly ahead of and behind the parent comet. And as you can see here, as the comet goes around the sun, the Earth will pass through that dense swarm of dust for a few years before and a few years after the comet is closest to the sun. I might say we can see some Leonids every year, but the best showers are only seen for a few years before and after the comet's return.
Every 33 years, in fact.
Indeed, every 33 years. Now, if we take a closer look at the point where the comet's orbit dives down through the Earth's orbital plane, the point we call the descending node, we obviously see where the Earth goes through there. And last November, in the situation here, the comet had gone by 258 days before, and we expected the Earth to go through and for the peak to be at the time when it was closest to the Earth's orbit. But that didn't happen. And the reason is that the extreme is not a simple cylinder of dust. It consists of many separate filaments. Every time the comet goes round and it's nearest to the sun, it lays down a new filament of dust. And then it goes away, and 33 years later it lays down another filament. Now, so we have a stream with all these filaments. Let's look at 4 different things that can happen. Here, the Earth is going through a fairly narrow, intense filament, and that might give a brief but strong shower. Here, the Earth is going through a much broader, less intense filament. And in this third example, the Earth goes through a gap between filaments, and we might see few Leonids at all. And in this fourth, more complex example, we go through a narrow filament first, and then a few hours later through a rather broader one. Now, what happened in 1998 was we went through this rather broad peak first, and if you look at the activity curve again, you can see there's the broad main peak, and that was some 16 to 18 hours before the expected peak. You can see the line there when we expected the peak to be, and then at that time we were going through a rather narrow filament of material. Now, in order to know what's going to happen at any particular year, we need to map the positions of those filaments within the swarm. And David Asher of the Armagh Observatory and his colleagues have done some really excellent work in mapping the filaments of dust within the stream. And they've, for example, shown that some of the major meteor storms of the past can be tied in with particular filaments. For example, the great storm that was seen in 1833, you can see the lovely woodcut here, was due to a filament of dust released just 33 years earlier, in 1800. Similarly, the great storm of 1966, that was due to dust released in 1899, 67 years earlier.
What about the bright meteors of 1998? When were they released from the comet?
Well, again, David Asher's work has shown that in 1998, the Earth passed through an arc of dust released as long ago as 1333, 666 years ago, and that this particular filament had moved away from the comet's orbit to be in just the place where the Earth passed through. You see, each time the comet goes round, it produces dust particles which have orbits similar to the parent comet, but significantly different from it. And it so happens that the 1333 dust had moved off so that we passed through it 16 to 18 hours before we expected. Now, the age of the filament explains not only why we got a large number of bright Leonids, but also why the peak is broad. See, the dust particles in the filaments are acted on by planetary perturbations and a number of other effects. One of these is called solar radiation pressure. The sun's radiation does exert a significant pressure on small dust particles, and it pushes them away from the sun. You can see that most clearly in the dust tails of bright comets. Here's a picture of comet Hale-Bopp taken by Rob Bullen in 1997, and you can see the broad curving dust tail there.
Lovely
And
picture.
that is caused by the radiation pressure pushing the dust particles away from the comet's nucleus. Now, in a meteor swarm, the smallest dust particles will be pushed away by the solar radiation pressure. In this animation, you can see the small particles are moving away from the sun, from left to right, leaving medium and larger particles, and eventually some of the medium-sized particles will be lost as well, leaving a preponderance of bright meteors. In addition, the older a filament is, the more planetary perturbations tend to broaden it. And so when you have a filament released in 1333 that's centuries old, you expect a preponderance of bright meteors, a broad peak, and that's exactly what was seen last year.
All right, John, now for the $64,000 question. What's going to happen this month?
Well, in the light of what happened last year, it's wise to be cautious.
Yeah, I agree.
But I think we do expect there to be an outstanding Leonid shower this year. I don't expect anything like the great storms of the past, because the mist distance is just too great. For example, if you can see on this graphic, the Earth distance from the comet's orbit is some 6 times further than it was in 1833, and 3 times further than it was in 66. So we don't expect a great storm, but certainly an outstanding shower. And the modelling of the stream has shown that we are going to pass quite close to several of the younger filaments of dust released in 1899, 1932. And this means that we expect a rather narrower, more intense stream this time, perhaps a shower lasting no more than an hour or two, and that it will be not as rich in bright meteors as before. Perhaps there will be many more faint ones at this time. In fact, the peak might be rather similar to that seen in 1866. You can see here that Leonid rates rise from a few hundred meteors per hour around midnight, peaking at several thousand meteors per hour just after 1 o'clock, and then dropping off again to several hundred meteors per hour by 4 o'clock in the morning. A narrow peak, fairly intense, rich in faint meteors.
When do you expect peak activity?
Well, we hope that, of course, it's not going to be like last year
Right.
and occur earlier or later than we expect. Again, the modelling seems to indicate that we will pass closely to those young, fresh filaments around the time we're nearest to the comet's orbit. That's about 2 a.m. on the morning of Thursday, the 18th of November. But it would be very wise to go out the night before, that's the Tuesday, Wednesday, and the night after, that's the Thursday, Friday, as well as the peak night, which is the Wednesday, Thursday, just in case, of course, the activity should come early or late. But the main night is early hours of Thursday the 18th.
One advantage also, the moon sets early, so no real trouble this time from moonlight. And of course, very useful work to be carried out, not with elaborate equipment, with the naked eye alone.
Yes, indeed. You don't need anything expensive equipment to observe meteors. You do need to be warm and comfortable, particularly important on November evenings and the early morning hours. And really, I can give no better advice than the advice we gave last year. Wrap up warmly. Several thin layers are much better than one thick one, and get into a sleeping bag. Make sure you wear a hat, because a lot of body heat is lost through the top of the head. And you'll also need gloves. And personally, I prefer fingerless mittens because they do give some freedom of movement. Recline at a comfortable angle in a deck chair facing southeast or south. Make sure you pick as dark a site as possible, well away from any street lights or other artificial lighting. Put your report forms on a clipboard and use a red torch like this cycle rear lamp for illumination. It won't ruin your night vision once your eyes have grown accustomed to the dark. Make sure you have set your watch accurately to a radio or telephone time signal. You'll of course need pens and pencils and a rubber. Some people like to tie these to the clipboard to prevent them getting lost in the dark. You'll also need a long wooden stick or a ruler to line up along the paths of any meteors you see. And of course a thermos flask of hot soup or tea as you wish. And then all you need is lots of patience.
You're sitting comfortably in your deck chair and you see a meteor. What do you do?
Well, you take your wooden stick and hold it up to the sky along the line of the meteor you've just seen. You then extend it backwards from the direction it came. And if it came from the Leonid radiant in the sickle of Leo the lion, it's a Leonid, like the animation you can see here. But if, however, when you extend it backwards, it misses the Leonid radiant, then it's a sporadic. So you need to record the time of the meteor you saw, whether it was a Leonid or sporadic, and the constellation in which you saw it. Now, you may like to record the brightness of the meteors measured against nearby stars, and you will see quite a lot of persistent trains left behind by the brightest Leonids. Now, this video shows you some background stars, and there's a slow-moving artificial Earth satellite moving across the frame from left to right, and here's a beautiful Leonid streaking from right to left, and you can see there it's left a persistent train or wake behind it, a trail of ionised gases in the upper atmosphere left behind as the meteoroid slams into the air at 71 kilometres per second. Now, those trains can distort over a number of minutes. Here's a lovely sequence of pictures taken by John Randall last November during the Leonids, showing a lovely train seen almost head-on, distorting over a number of minutes. It's a lot of information to record in just a very short piece of time.
It certainly is. Now, supposing we're lucky and we have a real storm, there are so many meteors, you're completely overwhelmed. What then?
Well, the first thing you could do is perhaps just record the time and whether it was a Leonid or sporadic. But if rates are so high you can't even do that, what we'd suggest is just counting the number of meteors you see in, say, 5-minute intervals crossing a particular area of sky. You might, for example, choose the bowl of the plough. Now, here's a photograph taken in 1966 at the time of the Leonid storm of the bowl of the plough. You can see Leonids streaking across.
Damn.
You'd count those Leonids going through the bowl of the plough, but not those outside it. Now, it's an awful lot of information to try and get down. A lot of people may be daunted. Well, we produced some instructions for Sky at Night viewers, and we've also produced a form which people can use on which to record their observations. We're suggesting that what people do is count the number of Leonids passing through the winter pentagon. That's the shape of stars made up by the bright star Capella in Auriga, Aldebaran in Taurus, Betelgeuse in Orion, Procyon in Canis Minor, and the twins of Gemini. And if you see a Leonid within that pentagon, or starting or ending within it, then you count it in your 5-minute interval. But any meteors outside the boundary, you don't count them.
And this kind of work can be very valuable indeed, so we're hoping the viewers are going to collaborate on this one. Well, John, where will you be?
I'll be in the Sinai Desert hoping for clear skies.
I'll be in Sochi and Sussex, also hoping for clear skies. So let's hope we have a really good shower. John, thank you very much. If you'd like some of our forms, then send your Saturday envelope into Leonid Information, BBC Television, Sky at Night, London, W12 7PS, and we'll send you a form. You can, of course, send to our website, www.bbc.co.uk/Sky at Night, or CFAX page 620. And by the next Sky at Night, we'll know whether we did or did not have a really good display of Leonids. When I come back next month, I'll be joined by Martin Mobley, and we'll talk about the wide variety of telescopes now available to amateur astronomers. Until then, good night.